Hello, ladies and gentlemen. Welcome back to day 6 of chapter 9. We are in section 9.3, day 2, putting it all together, 2 sample z-tests for piece of 1 minus piece of 2. By the end of this lesson, you'll be able to perform a significance test about a difference between two proportions, and I would like for you to try these problems at the end of our lesson. Let's go ahead and begin. As I said, we are on 9.3, day 2, putting it all together, 2 sample z-tests for piece of 1 minus piece of 2. And you can read much of this information on pages 631 to 635. Now, let's start with the question, is it okay to use your calculator for the do step, and are there any drawbacks? Now, yes, you can use the calculator to double check your work, but not if you're going to earn full credit. If you want to earn full credit, you actually have to show your work. Also remember that the x values, the successes that you put into the calculator, need to be integers. The calculator will not accept decimals. All right, let's try our example. So, are teenagers going deaf? In a study of 3,002 randomly selected teenagers in 1994, 15% showed some hearing loss. In a similar study of 1,799 teenagers in 2006, 19.5% showed some hearing loss. Now, for letter A, between the two studies, Apple introduced the iPod. If the results of the test are statistically significant, can we blame iPods for the increased hearing loss in teenagers? Now, the thing that you need to keep in mind is that if you randomly select from a population, you can infer about the general population. If you randomly assign treatments in a well-designed randomized experiment, then you can determine cause and effect. Now, the type of randomization that we have in these two studies is randomly selecting from a population. No experiment was done. That means that no, we would need to conduct a well-designed randomized experiment to infer a cause and effect relationship. We cannot blame iPods for the increased hearing loss in teenagers. And now let's actually do the test. So for letter B, do these data give convincing evidence that the proportion of all teens with hearing loss has increased? Now, for the hearing loss to have increased over time, we would want to look at the hearing loss currently and compare to the hearing loss in the past. And if we start with the hearing loss from 2006 and subtract the hearing loss from 1994 from that, then we can actually use a positive difference to show an increase in hearing loss. All right, so we want to test the following using alpha equals 0.05 level. Null hypothesis is piece of 1 minus piece of 2 equals 0. In other words, the true proportion of teens with hearing loss from 2006 minus the true proportion of teens with hearing loss in 1994 is equal to 0. Another way to write this would be piece of 1 equals piece of 2, that basically they're exactly the same. If hearing loss hasn't increased, then they're the same. Now, since we're trying to find evidence of the hearing loss increasing, if there's a higher proportion of hearing loss in 2006 compared to 1994, then our difference should actually be positive. That's why I'm using greater than 0. Basically, the true proportion of teens with hearing loss in 2006 should be greater than the true proportion of teens with hearing loss in 1994. Right? And over here, I have those two parameters actually defined, where piece of 1 equals the true proportion of teens with hearing loss in 2006, and piece of 2 equals the true proportion of teens with hearing loss in 1994. All right, so I have my significance level, both hypotheses, and my parameters of interest defined. I have all 3 portions that I need for my state. Now for the plan, I need to name my test first. I'm going to be doing a 2 sample z-test for piece of 1 minus piece of 2. And the first condition that I always check is random, because if we haven't randomly selected the individuals or randomly assigned treatments, then there's no point in doing anything further. All right. Now, we do know that 2 independent random samples were taken in 2006 and in 1994. Now, because we were sampling from finite populations without replacement, we also need to check the 10% condition to ensure that the independence of these independent random samples is still actually preserved. All right, so it is reasonable to assume that 1,799 and 3,002 are less than 10% of the teen populations in 2006 and 1994, respectively. Using the word respectively here allows you to state that we're talking about these numbers in the same order that they're written in. So the 1,799 is associated with the year 2006, and the 3002 is associated with the year 1994. Right, that allows us to write this in just one sentence. Now, for the large counts condition, we need to use our combined or our pooled sample proportion. Now, for that, we first needed to find what our number of successes were in each sample. So in 2006, we had a sample size of 1,799 teenagers and a sample proportion of 19.5%. That would be, the percent was 19.5%, the proportion would be 0.195. I just take this divided by 100 and you'll have the correct proportion. And so I'm taking 1799 times 0.195, and that's how I'm getting approximately 351. Now this was actually 350 point something, but I'm rounding to the nearest integer so that if I want to use the calculator to check my work, it's a lot easier to do so. Also, you can't have partial people. Now for my second successes from 1994, 3,002 teenagers were randomly selected in 1994, and 15% showed hearing loss. So I'm taking the 3,002 times the 0.15 to represent the 15%, and that equals approximately 450 teenagers with hearing loss. Now for your pooled proportion, you need to take the successes from both samples, add them together, and the sample sizes from both samples and add them together. The totals of each of these, the total successes and the total sample size, when you divide that, gives you your pooled proportion. Now the only reason that we are calculating this is that our null hypothesis is making us assume that the true proportions from each year are exactly the same. If they're exactly the same, there's no reason to keep these samples separate when we're going through and working through our problem. That's why we actually pool these. But it's only this assumption that these two are actually equal to each other that makes us pool. All right, now when we divide this out, we get about 0.1668, and that's what I'm going to use in my large counts condition. All right, so I need to take my sample size times my pooled proportion, so 1,799 times 0.1668 equals approximately 300, and 1,799 times 1 minus 0.1668 equals approximately 1,499. Right? That's my successes and failures for the first samples, my expected successes and failures, I guess I should say. Now, from 1994, we have the 3,002 for our sample size times our pooled proportion, so 0.1668 gives us approximately 501 successes. And then 3,002 times 1 minus our pooled proportion is equal to approximately 2,501 for failures. So successes and failures in both samples, the expected values, are at least 10. This allows us to assume that the sampling distribution of p hat sub 1 minus p hat sub 2 is approximately normal, which allows us to use the normal curve once we find our z-score. Now that we know that all of our conditions are met, we can go on to our do step. And for that, we need our statistics. And let's see. P hat sub 1 is the 0.195 from this 19.5%. That's why I have this highlighted in pink down here. And my p hat sub 2 was this 15%. As a proportion, it's 0.15. That's why I have this highlighted in orange. And then minus 0, it's your statistic, which is the difference of both my p hat values, minus my parameter, which is the difference of p sub 1 minus p sub 2, but we're assuming that that difference is equal to 0. All right, so the 0 is actually the difference of these two already worked out with our assumption. That's why there's the 0 there. Now all this is divided by the square root of our pooled proportion times the complement of our pooled proportion divided by the first sample size, plus our pooled proportion times 1 minus our pooled proportion divided by our second sample size. So all of this is within the square root. And I just put all of this into my calculator and round my z-score. So let's take a look at that. So if I open this up with alpha y equals, hit enter, open parentheses, 0.195 minus 0.15, close parentheses, minus 0, and then arrow down to the bottom and open my square root sign, fraction, 0.1668 times 1 minus 0.1668, 1799 in the denominator, add another fraction into here, 0.1668 times 1 minus 0.1668, close my parentheses, and then my second sample size of 3002. And now I can hit enter, and this is how I got approximately 4.05. It was actually 4.0485 and so on. I've used the 8 to round the 4 up to the 5. Now this is a very large z-score, and we were looking in the greater than direction. So if I were to sketch my normal curve, just a standard normal curve, 4.05 would be very far on the right-hand side of this curve. And going greater than that would be shading off to the right, going off towards positive infinity. This is why when I'm calculating my p-value is the probability that we have a z-score greater than 4.05 from the standard normal curve. Using technology to calculate this, normal CDF, my lower bound was 4.05, my upper bound was positive infinity, just a very large number. Mu is equal to 0, standard deviation of 1. And if I type that into my calculator, so second vars to get to distribution, second option is normal CDF. And I have 4.05 in here. I have a very large positive number for my upper bound to represent positive infinity. 0 and 1 for my mean and standard deviation. Paste this in. And you get this number. Now be careful with this. Notice that it's not possible to have a proportion that is more than 1. That means I need to look over on the right-hand side here where it says this e negative 5. Now, e negative 5 stands for times 10 to the negative 5th. When you have a negative exponent on your times 10 in your scientific notation, instead of multiplying by 10 repeatedly in order to get the original value, you actually need to divide by 10 repeatedly. Now, the first time you divide by 10, let's say we approximate this at like 2.56. If I divide that by 10, my decimal point moves 1 to the left to become 0.256. And then every 10 that I divide after that, a 0 appears between the decimal point and the previous number. So if I divide by 10 3 times from this original value in scientific notation, I would actually have 2 zeros between my decimal point and the 2, because the first time I go around the 2 and then I start including zeros. Now once you divide by 10 for the 4th time, you end up with scientific notation again, which means that you can't use this just to figure out how many zeros go here, but you can use that pattern. Essentially, anytime you have scientific notation, you're going to use the first division by 10 to move around the integer at the front, and then the remaining division by 10s, in this case 4 more division by 10s, are going to become the zeros between the decimal point and the 2 here at the beginning. So that's how I'm getting 0.0000, notice the 4 zeros there, 256. Now for our conclusion, since our p-value is small, right, 0.0000256 is less than our alpha, our significance level of 0.05, we reject the null hypothesis. Now this is because we have convincing evidence that the true proportion of all teens with hearing loss has increased from 1994 to 2006. Right. Now if you wanted to check these values using the tests, let me arrow down here, we would go to Stat and over to Tests, and it would be a 2-prop z-test that we would be using. X sub 1 represents our number of successes from our first sample. So I would type in 351. My sample size would be the 1799. My successes from my second sample, 450. And my sample size, 3002. I want the greater than sign here. If I were to add p sub 2 to the other side, I would have p sub 1 is greater than p sub 2. And that's what this is saying, p sub 1, and then I want to choose the greater than p sub 2 side of this. All right, now you can go to calculate, or you can go to draw if you want to actually see how this gets sketched out. So it's sketching out my normal curve, and it's showing me the z-score. The p-value is so small it's approximately 0. And it's not really even showing the shading because it's so far out there, it's beyond the 3 standard deviations. All right, that's why I didn't actually show my 3 standard deviations within the sketch. You can also just do the calculate side of this, and it gives you a whole bunch of information. It's now, one moment. Test. Okay, so it doesn't even give you an option for pooled or not pooled. Interesting. I just want to pull those numbers back up real quick. All right, so my z-score is approximately 4.06 or 7, and that's because I was approximating this p hat sub c value, which means that this ended up actually being just a little bit larger. Now notice that this is still a very small p-value, and our first proportion was about 0.195, our second proportion about 0.1499, so these would round to the correct values. And p hat here is our p hat sub c. Notice that it matches what I'm using here. Right? And then gives us our sample sizes. So we have our z-score, we have our p-value, and we can double check the individual sample proportions and the pooled proportion that's calculated right there. In older calculators, you actually had to choose whether you wanted to pool or not pool, and that choice was always made based on whether or not you were using p sub 1 minus p sub 2 equals 0, and assuming that those were actually equal to each other. All right, now the final step for this one is interpreting the p-value from part B. All right, now the interpretation of the p-value is assuming that the null hypothesis is true. The p-value is the probability of achieving our sample results or more extreme in whatever direction our alternative hypothesis is going. So putting that into context here, assuming that there is no difference between the true proportions of teens with hearing loss in 2006 and 1994 respectively, there is a 0.000256 probability I'm just going to say chance. Of getting a difference in proportions of 0.045 or more. That's the actual difference between these two if you go through and you subtract them. So this answer was 0.045 that I'm referencing here. So that same difference or more, difference in the sample proportions or more basically. All right, go ahead and try these problems and we'll see you in class.